Alright, so we come back. We were talking about von Neumann stability analysis of advection equation. We had an expression like this, where we replaced all the discretized time and spatial variables. We replaced all of them by a perturbation in the form of some c raised to n power and an exponential of ikxj. This was the expression we got, and now the goal is basically to find for xc and see how that xc changes over time. If xc grows over time, then our method will be unstable because any perturbation is going to grow over time, and the error is going to increase. If xc shrinks in time, that is a stable method because any error is going to decrease. So now from here we can simplify. We can cancel out all the exponential terms. ei and kxj is going to be cancelled from both sides. So we can also cancel xc raised to n power. So what we have is, from the left side, from this term we get xc, from this term we get 1, from these two terms we get 1 from the first, and then we get exponential of negative ikxj minus xj minus 1. So if you cancel out eikxj from every term, this term doesn't have it, so you have to subtract it, and then you end up having eikxj minus 1 minus xj, where that is going to be minus del x. So because, as I have here, xj is going to be, or xj minus 1 is going to be xj minus del x. So anyway, this term turned out to be exponential of minus del x times ki. Now let's rename v delta t del x as alpha. Then we can rewrite this equation like so. C is equal to 1 minus alpha times 1 minus exponential of del x times k times I. Alright, the goal is to find xc and see how xc changes with respect to position, or maybe with respect to time. So we're going to solve for xc here. We're going to convert our exponential to sine and cosine using Euler's method. So now xc is going to be 1 minus alpha times 1, and then minus, this thing is going to be cos k del x plus I, the imaginary number, and then sine k del x. Alright, so this whole thing is an imaginary number. This piece is the real part of it, which is 1 minus alpha plus alpha cos del x, and this piece is the imaginary part of it with the negative minus I alpha up front. So we want to find the magnitude of this. Because xc is just this number, we want to look at the magnitude of xc and how that magnitude changes. So we multiply this complex number by its conjugate, and we know that xc times its conjugate is going to be the magnitude of xc raised to the second power. We want to limit that magnitude to be less than 1 to have a stable method, because if this thing is bigger than 1, then perturbation magnitude grows over time, and then it's going to spoil the solution. So that's why we need to limit the magnitude of xc to be less than 1. And the magnitude of xc is nothing but xc times its conjugate. So if you multiply this thing by its conjugate, then you get the real part squared, that's the real part squared, plus the imaginary part squared. So here's the imaginary part squared, which is alpha sine k del x. This needs to be less than 1, and we're going to simplify this a little bit. We're going to expand this quadratic term. We get 1 from the first, plus the second piece is squared, minus the first, 2 times the first times the second, so minus 2 times 1 times alpha, 1 minus cos del x. And then plus the second piece. This needs to be less than 1. We can cancel the 2 1 from both sides. We also factor out alpha squared from these two terms. So we get alpha squared. From here we have 1, and then we have cos squared of k del x. We also have sine squared of k del x, so these are going to be 1 again, so 1 plus 1 is going to be 2. And then minus 2 times the first times the second, so it's minus 2 times cos del x. So these two end up being 2 minus 2 times cos del x, and then minus 2 alpha, the rest of it. Alright, so if you look at these, I mean, the total sum has to be less than 0, because we cancel the 1 from both sides. Alright, now we know that 1 minus cos del x is always positive, because cos del x is always less than 1, so we can cancel these two. And then what we get is alpha squared from here, and then minus alpha from there. And then 2 also cancel out. You can simplify both sides, divide through by 2. Alright, so this needs to be less than 0 to have the magnitude of c less than 1. Let's look at alpha. What would be the alpha such that we get this less than 0? So this thing means alpha times alpha minus 1 less than 0, and so to have this thing negative, alpha should be between the two roots. So this is a quadratic algebraic equation. For this thing to be less than 0, then alpha should be between the two roots. And this thing has two roots, alpha equals 0 and alpha equal to 1. So the condition would be alpha between 0 and 1. What was alpha? Alpha, if you remember, was the velocity of the flow times the interval in time divided by interval in x. So v del t del x. That has to be less than 1. So let's understand what this means. This is called, by the way, Courant-Friedrichs-Lewis condition. So from now on, we're going to call it Cfl condition. The Cfl condition relates the spatial discretization downstairs to temporal discretization to have a stable method. Okay, so again, Cfl condition is a condition between the spatial and temporal discretization such that we get a stable discretization and our error won't increase in time. Alright, so let's understand what this means. So I have a picture here, or a drawing. So imagine my horizontal axis is the x-axis, and I have interval del x between 2 points. So these are x points. And I'm going to have my time axis on a vertical axis. So if I have a set of x points along the x, that is going to be a time, let's say tn. And then I'm going to have another set of 2 points up here as the same coordinates, but now in the next time point. So what we are doing here is that we are relating the values of u at these 3 points, which is u, ujn, uj minus 1, and n, and u. So this is uj. Well, actually, I have the indices here. So this is uj at time n. This is uj plus 1 at time n, and this is uj and uj minus 1 at time n. So these are all at time n. So what we are doing is that, let's say in here, I'm using these 2 points, j and j minus 1, to predict uj at n plus 1, that term. Alright, so depending on the velocity. If velocity is let's say positive, I'm using this term and that term. These two, I'm using the information from these 2 points to predict that point, which is uj n plus 1. And if the velocity is negative, then I'm using j and j plus 1, these 2 points, to predict the same point. So you can either stick to the left side or right side of this triangle. So the point is, we have to use the information on this line to get the information on the next time point. So if I calculate this angle, which is nothing but the distance between these 2 points, which is delta x, divided by this distance, which is delta t. Remember, the distance between this axis and the axis above would be exactly the time interval. Alright, so this angle, as I have here, is going to be del x divided by del t. So what we are saying is that v, let's correct our condition, I can actually reorder this and then say v should be less than or equal to del x over del t, something like this. So the v should be less than del x over del t. V is the physical velocity. Del x over del t is the numerical velocity. It's something that we calculate. This is coming from the physics. This is coming from the problem information. This is just what we calculated. This has nothing to do with the physics. This is how we discretize the equation. This is math, that is the physics. So the real velocity should be less than what we predict as the prediction for the velocity, right? This is the condition we're getting. We were saying that if this holds, our method will be stable. And let's look at this graph again. This angle, as we discussed, is the tangent of that angle is going to be numerical velocity, or the mathematical prediction for the velocity. What we are saying is that this angle should be less, this should be greater than the angle that is coming from the actual velocity. So that means if I have a wave and this wave propagates in the space, the speed with which I calculate the information, the progression of the information in time, should be less than the physical speed. It means I cannot predict something that hasn't happened yet, mathematically, alright? So the condition of this angle being greater than that angle, which means del x over del t should be bigger than the physical velocity, means that the real information should propagate faster than what y calculates. So the black diagram here is what we calculate numerically, and then the red one is what is happening physically. So physically, the information is moving in time faster than what I calculate, which is making sense. So we cannot bypass the time. So that's what the condition is saying. All right. So from now on, we're going to refer to the Cfl condition to have a stable discretization or stable numerical technique. All right. So let's go back to our differential equation. We had the discretization in time, forward in time, and this is the forward in space. We move everything to one side, and we remove the well, so actually I forgot to say something, and that is, so for explicit methods, remember we did the explicit discretization time. For explicit methods, we always need to worry about stability, and that's why we talked about this one moment stability analysis. Now, on the other side, if we use implicit methods in time, then we do not have any stability problem, and so we do not need to basically do this one moment stability analysis to come up with a relation between del t and del x. So here we're going to look at the backward Euler version of what we just saw. So if I do the backward Euler in time, du dt will be discretized at uni minus un minus 1 divided by del t. This is du dt. And the right side has to be at time n to be backward Euler in time, right? So I'm going to discretize this right side at time t equal n. So that's why I have n index for the time index, and the other ones are just forward in the space. So what I'm doing is I'm doing backward in time and forward in the space. So this is going to be implicit in time, and we are claiming that this is stable. That means if you do the one moment analysis on this, we would say that the magnitude of that perturbation, that c, we're going to say that c will not grow in time. So let's dive into the details of how we can calculate this. So in the next video, part 3 of this partial differential equation solution using numerical techniques, we're going to look at the stability analysis of backward Euler in time and forward Euler in space. So stay tuned, and thanks for watching.